Have you ever wondered what quantum decoherence is? Well, to understand that, let's first dive into the realm of quantum physics. This is the science of the exceptionally tiny, the world of particles so small that they make atoms seem gigantic in comparison. It's a realm where the traditional laws of physics that govern our everyday world cease to apply, and the strange, often counterintuitive principles of quantum mechanics take over. Quantum physics is all about studying these minute particles, the essential building blocks of the universe. It's about protons, neutrons, electrons, and even smaller particles that you might not have heard of, like quarks and leptons. Now, within this field, there's a phenomenon called quantum decoherence. It's a complex term, but don't worry, we're going to break it down. It's a fascinating concept, and it's at the heart of many of the most cutting-edge developments in physics and technology today. Quantum decoherence is a complex yet fascinating concept that we are going to explore today. To understand quantum decoherence, you need to first grasp the concept of quantum states and superposition. Now, you might be wondering, what are these quantum states? Well, in quantum physics, a quantum state is the state of a quantum system which provides a probability distribution for the outcomes of each possible measurement on the system. It's like predicting the weather. We can't say with absolute certainty that it will rain, but we can discuss the likelihood based on the current state of the atmosphere. Now let's move on to superposition. It's a fundamental principle of quantum mechanics that allows particles to exist in multiple states at once. Imagine you have a coin. In the classical world, it can either be heads or tails. But in the quantum world, it's like the coin is both heads and tails at the same time, until you look at it. This is the concept of superposition. It's like Schrödinger's famous thought experiment with the cat that is both alive and dead until you open the box to check. Superposition is not just theoretical. It's been observed in the lab, from tiny particles to larger objects. And it's the principle that powers quantum computers, which can process vast amounts of data simultaneously because each bit can be both 0 and 1 at the same time. However, superposition is a delicate state. It's easily disturbed by its environment, a process we call decoherence. When a quantum system interacts with its surroundings, the various possible quantum states interfere with each other, leading to a definite state. It's like the coin finally landing on heads or tails, or the cat in Schrödinger's box being found either alive or dead. In the quantum world, particles can exist in multiple states at once, until they interact with the environment. This is superposition, but when this delicate balance is disturbed, we get what's known as quantum decoherence. Quantum decoherence occurs when this superposition of states is lost. So in the next scene, we'll delve into the process of quantum decoherence and the factors that cause it. Now, let's delve into the process of quantum decoherence. Quantum decoherence is a fascinating phenomenon that occurs when a quantum system, say an electron in a superposition of states, interacts with its environment. This interaction causes the system to lose its quantum superposition, its ability to be in multiple states at once. Let's break this down a little. Picture a quantum system as an isolated entity, floating in a sea of potential states. This system can exist in a superposition of states, a unique characteristic of quantum mechanics. Now, when this system interacts with its environment, for instance, other particles or fields, it begins to lose this superposition. But here's where things get interesting. This loss of superposition is not a simple transition between quantum states. Think of it less as the system choosing a single state and more as the system losing its quantum nature. It's like our quantum system is shedding its quantum cloak, revealing a classical system underneath. This is largely due to the fact that the environment is continually measuring the quantum system. In the quantum world, a measurement forces a system to choose a state. So when our quantum system is constantly being observed or measured by the environment, it essentially becomes pinned to a single state. It's as though the quantum system is being forced to play by classical rules. So why is this important? Well, quantum decoherence is one of the main obstacles in the development of quantum computers. Quantum computers rely on superposition to perform complex calculations at incredible speeds. However, maintaining superposition is a delicate balancing act. The moment a quantum bit or qubit interacts with its environment, it risks quantum decoherence and the loss of its computational power. In essence, quantum decoherence is the transition from a quantum mechanical system to a classical one. It's a journey from the strange and wonderful world of quantum mechanics to the familiar realm of classical physics, a journey that's at the heart of our quest to harness the power of the quantum world. You might be wondering, why does quantum decoherence matter? Well, the significance of quantum decoherence is most apparent in the pioneering field of quantum computing. Quantum computers promise to revolutionize computing by performing calculations at speeds that dwarf those of our current technology. This is possible because of a quantum bit, or qubit, which, unlike a classical bit that can be either a 0 or a 1, a qubit can be both at the same time. This is thanks to the principle of superposition. But here's the problem. When a quantum system interacts with its environment, a process known as quantum decoherence, the superposition collapses, and the qubit becomes simply a 0 or a 1, just like a classical bit. In essence, quantum decoherence is the primary villain in the story of quantum computing. It's the process that leads to the loss of quantum information, and it poses a significant challenge to the development of quantum computers. If we can't prevent decoherence, we can't maintain superposition, and without superposition, a quantum computer becomes just an overly complicated and inefficient classical computer. Imagine you're baking a cake, and every time you open the oven to check, the cake collapses. That's quantum decoherence for you. It's the unwanted guest at the quantum party, turning all the superposition streamers into just plain old streamers. But it's not all doom and gloom. Scientists are working tirelessly to understand and manage quantum decoherence. They're developing techniques to minimize its effects and prolong the lifetime of quantum states. The better we understand quantum decoherence, the closer we come to building practical quantum computers that can solve problems beyond the reach of classical computers. So in a nutshell, quantum decoherence is like the sand slipping through the fingers of quantum computing. It's the phenomenon that turns the quantum magical into the classical mundane. But it's also the dragon at the gate that we must understand and conquer to unlock the fantastic potential of quantum computing. Therefore, understanding and managing quantum decoherence is crucial for the advancement of quantum computing. Let's summarize what we have learned about quantum decoherence. It's a term that might sound straight out of a science fiction novel, but it is deeply rooted in the reality of quantum physics. Quantum decoherence, in essence, is the process by which a system loses its quantum mechanical properties. It's like a quantum whisper becoming a classical shout. We've journeyed through the microscopic realm of quantum states, where particles can exist in multiple states at once, a phenomenon known as superposition. Imagine a coin spinning on a table, simultaneously displaying both its heads and tails until it lands. That's the quantum world for you. A world where possibilities coexist until observed or interacted with. This leads us to the heart of quantum decoherence. An isolated quantum system can exist in a superposition of states, but when it interacts with the environment, information about the system leaks out. This interaction causes the quantum system to rapidly lose its superposition, a process we call decoherence. It's like our spinning coin abruptly landing flat on the table, showing either heads or tails, but not both. Quantum decoherence isn't just a curious phenomenon, it has profound implications, particularly in the world of quantum computing. Quantum computers operate on qubits, which can be in a superposition of states. However, the susceptibility of qubits to decoherence presents a significant challenge. It's like trying to perform a delicate ballet while surrounded by a mosh pit. The chaotic environment disrupts the carefully choreographed dance of quantum states, potentially ruining the performance. This is why scientists are putting in tremendous efforts to understand and minimize quantum decoherence. It's an obstacle, yes, but it's also our key to unlocking the full potential of quantum computing. And with that, we've come full circle. Although quantum decoherence may sound like a complex concept, it is an essential part of understanding the fascinating world of quantum physics. So next time you hear about quantum computing or quantum physics, remember the spinning coin, and you'll have a glimpse into the strange and wonderful world of the quantum realm.